and thanks everybody. Hi to the people out there as well. Okay, so yeah, before I start, I like handouts in talks, but I also don't like carrying lots of paper around, so I always kind of put the slides online, and I'm unclear whether people like that or not, but what I've been doing for a while is using a bit.ly code, but people don't seem to take it up very much, and I've talked to people and they say it's too much effort to kind of type those letters in. So I've gone for an even simpler thing now. Were you doing it? Did the slides come up?
Yes. Yeah, I've got them.
All right, so the QR code is popular. Okay, good. All right, so if you scan that QR code, you'll get a copy of the slides. I'll leave it up for a little bit. Unfortunately, there was supposed to be the bit.ly address on here as well for people online to look at, but it's not there. I didn't think that through entirely. Okay, so I'll put this up again in a second, but I'm going to go up to the main talk, or the first slide. So I'm going to talk about a fairly long piece of work that I did with Niels Linnemann and Mike Schneider over the past year and a half now, really. This was sort of partly for us sort of a pandemic activity when we were online and could work together. So there's a paper on the archive that's there. It's actually been kind of, we're in the middle of editing it and revising it. We're not going to change any conclusions substantially, but various things I hope are clarified and more accurate. So, my usual disclaimer, which some people will have heard before, everything in the paper we have all the words in the paper we have a consensus on, but I'm not just reading the paper, so today it's my words, so I think we're basically in agreement with what I'm going to say, but there was a fair amount of negotiating and I would not commit them to the very words that I say today. Okay, so there's the QR code again in case there's people on Zoom who want to point their phones at it or devices at it or take a screenshot and get hold of the slides to look at. So I'm going to start with a bit of background, and then before I give an overview of the talk. And when you're talking about, what I'm going to talk about today is an attempt for a real practical experiment, arguably in quantum gravity. And so it's worth sort of locating it in sort of general thought about what it is to do experiments or to make observations in quantum gravity. And the way that sort of discussion usually starts is by pointing out that it's sort of extremely hard to do experiments in quantum gravity in a certain sense. Although one needs to, there's been a fair amount of recent discussion, and David Wallace has sort of pushed some of this discussion recently. One needs to be rather more, it needs to be somewhat nuanced about this, and there have been rather, I guess, sweeping statements that people like me, including me, probably have made that aren't strictly accurate. So, I've always said this part. One of the things that one of the predictions of whatever theory of quantum gravity you have has got to be that general relativity in the regimes in which we've tested it is true, and similarly quantum mechanics, quantum field theory in the regimes in which we've tested it are true. So that's clearly supposed to be a prediction of quantum gravity, and there's work understanding in that direction in the various theories, and those are important questions. There's also an important kind of distinction, one needs to be clear, have some clarity in what one means exactly by quantum gravity. And this is kind of Wallace's point. So, two kinds of things you might mean. One is you're thinking about string theory or loop quantum gravity or one of the other approaches to quantum gravity. And what you mean is a theory of quantum gravity that will be valid to high energies, say to sort of Planck scale and beyond physics. But there's a lot of physics that's both quantum and gravity in the low energy with respect to that regime. And we really do have a theory that makes predictions in that regime. So basically a theory where you linearize general relativity and quantize. We have a quantum field theory, and this is now thinking of quantum gravity as an effective field theory, and there are many predictions there. Now, so Wallace talks about this. There's an earlier paper by Burgess that sort of makes sort of similar points. Lots of these kinds of predictions are not in classical general relativity or quantum mechanics in, say, flat space-time regime, or in classical space-time regime, sorry, flat space-time regime, but exist in the semi-classical gravity sector, where one basically has to take the expectation value of energy momentum and feed that into something like an Einstein equation, but one can compute solutions for that. And in that way, this is how stellar evolution, for instance, is modeled. So there's even predictions that go beyond semi-classical gravity. And again, this one Wallace talks about. If you want to understand, or the standard way of understanding some of the structure in the microwave background, involves thinking about what's happening, or describing what's happening in the early universe, and assumes an inflaton field and the interaction with the inflaton field with the space-time geometry. And that calculation is not just a semi-classical one, but also involves treating the geometry as quantum, as gravity itself as quantum. Of course, this is still, even in this case, way outside the sort of string theory or loop quantum gravity, high energy quantum gravity. This is still this kind of account of CMB structure is again still in this treating quantum gravity and in the effective field theory approach. Okay, this example is kind of nice because, well, what I'm going to talk about is arguably also involves having to think about space-time or gravity superpositions. We'll see it's controversial whether it does, and that's part of what I want to talk about. But also, it's also cleaner than this because, if you think the observations of microwave background are giving you evidence or are showing you the quantum nature of gravity for this reason, because we have gravity superpositions, quantum superpositions, well, that's a conclusion you can draw, but it's very dependent on some background, some relatively controversial background theory, namely about the theory of inflation. The example I'm going to talk about uses much more simple physics. Okay. So what about that kind of experiment? So I'll give you an outline of what we're trying to sort of think of. If you wanted to observe the quantum nature of gravity, see some physics beyond semi-classical gravity in the laboratory, how might you go about it? Well, it's good to have sort of electromagnetism as an analogy in the back of your mind, because in fact, it's a very strong and kind of deep analogy. So the first thing you might think is, what's the characteristic quantum effect in electromagnetism? And of course, it's the photoelectric effect. But it's clear there's no hope of observing a kind of gravitational version of the photoelectric effect. For instance, you think about hydrogen. Well, so if you just consider the sort of potential, electrical and gravitational potential energies between the first and second excitation levels for the electron, it's about 10 electron volts is the electrical potential, but the gravitational potential is 39 orders of magnitude smaller than that. So that's not really going to happen. We're not going to see photons produced because of the loss of gravitational potential energy. So, okay, what other kind of characteristic quantum effects are there? Well, you know, systems gravitate. Suppose you had a system in a superposition in different places, then it's going to be interacting with the gravitational field if things, especially if things are moving. So one might sort of think, well, look, if they're moving, maybe they're going to produce gravitons, and now I'm going to lose, because of that, I'm going to lose coherence in a quantum superposition of the state, because I'm going to have to trace out over the gravitational field. I'm going to end up with an effective mixed state. I'm going to get decoherence because my body masses are interacting with the gravitational field and producing gravitons. Okay, just as we get decoherence when things interact with the electromagnetic field. Even that's an incredibly hard and difficult experiment to do. People have sort of thought about that, and the technology to do that is a long ways off, but maybe not impossible. But there's a class of experiments that people have been talking about for the last 5 years now, which actually seem much more within reach. You know, the optimists in the community sort of talk about a decade, something like that, to actually do these experiments. So, and this kind of comes because you think about all the Planck quantities. The Planck energy, incredibly high, the Planck length, incredibly small. But the Planck mass, it turns out, is actually on a very kind of human scale. As I said here, it's about 10 micrograms, which is, well, the nice example is it's like a centimeter of hair or something like that. Rather more disgustingly, it's about the mass of a flea egg. So these things here, you know, have the Planck mass. Okay, so that's kind of a regime where you might expect to see gravitational and quantum effects, just sort of naively. And in fact, that's the case that I'm going to be describing. So from an experimental point of view, as you probably know, over the last few decades, people have put effort into putting larger and larger objects into quantum superposition and maintaining quantum coherence for larger and larger systems, seeing their quantum nature. So you're sort of thinking about the Planck mass, and basically what's happening from below in terms of mass is heavier and heavier things experimentalists are able to keep in quantum superposition. On the other hand, people have, in the same period, been interested in observing gravitational effects of smaller and smaller things. Part of this sort of started when people were interested in whether there would be deviations from Newton's law because of extra compactified dimensions and stuff like that. But people have, in fact, been doing gravity experiments and seeing the gravitational effects of lighter and lighter things. And so the sort of general picture is we're kind of getting to a point where these two regimes actually meet, and we can try to do an experiment that has both features. Okay, so objects like that, supposing we're able to, they're small enough, as I say, to maintain quantum coherence, but heavy enough so that their gravitational effects actually have an effect. Obviously, it's going to be part of this, and I won't sort of keep saying this, but not only does they have to be heavy enough that their gravitational effects can be observed, it's also, of course, they're going to have to be neutrally charged and things like that, and no van der Waals forces, so that gravity is really the only force that they're experiencing or exerting on one another. So if I've got those conditions, well, there's this unpleasant term, gravcats, but we'll use that, short for gravitational Schrödinger cats, for the obvious reasons. So that's what I mean by gravcats. Okay, something that has those properties. Okay, and I'm going to explain to you the experiments one can do, hopefully, to actually observe, using these to observe the quantum nature of gravity. Okay, so very quickly, here's sort of the outline. I know that was a fairly long introduction to how things, how things are going to go, to the background. I'm going to just explain to you in a very naive way what the experiment looks like, so that you have a feel for it. Basically, this is just sort of undergraduate physics, so you get the basic idea. Probably going to have a lot of questions at that point, but even at that level of analysis, these experiments are going to be interesting because I want to explain how they, in fact, must lie outside the regime of semi-classical gravity. But what we need to do at that point is go back and think about the experiments from a more fundamental point of view, bring in some more fundamental physics to try to see better what's actually going on in them. And what we see when you do that is there are actually two ways of looking at these experiments. One, the Newtonian, one, the tripartite. And it turns out these different frameworks, they start from the same point, but actually come up with different models of what's happening in the experiment, and actually then have different interpretations of what's happening in the experiment. Okay, so that part's all physics, and really, I don't have anything really terribly new to say here. I mean, I sort of have a certain way of packaging things, but this is all physics that's in the literature. And if I can talk a bit more quickly than I have been so far, then we'll talk about sort of the added value here, the sort of interpretation of what's going on here and how you should think about it. And in particular, our take on how one should think about this disagreement or apparent disagreement about what's going on in the experiment. That's kind of the payoff. And then the part where I sometimes don't get to, I'll talk more about other ways of thinking about the value of this kind of experiment. I mean, aside from just being kind of cool. So, okay, let's jump right into the physics. And again, first of all, I'm going to call this the naive model. So it's the first of three models, three approaches to understanding what's going on in these experiments. This one's really just a sort of very easygoing sort of first pass, just so you can see what's predicted. So, imagine you have, this is the proposal for the experiment schematically. So imagine you have two gravcats. So I've got one over here on the right and one over here on the left. And each of them is going to be put into a spatial superposition of left and right parts. Okay, like this. So maybe we'll call this gravcat 1 and this gravcat 2. So that's got two gravcats, each of which is in spatial superposition. So perhaps they have spin and I put them through a Stern-Gerlach apparatus. Okay. Very gently so that they are indeed in superposition and it's a coherent quantum state. So we can write down the state like this. Okay, so I wrote it, but I didn't change it. It's okay. So just for how to read these equations, I didn't put any subscripts on. Terms you see to the left of the tensor product refer to this gravcat 1. Terms you see to the right of the tensor product refer to gravcat 2. So I have gravcat, and obviously normalization we're just going to sort of ignore. That's not going to affect anything. So I have gravcat 1 in a superposition of the left and right positions. Suppose the mean position is minus d, and then there's a displacement of delta either side to represent the left and right. And similarly for gravcat 2. Okay, so it's a superposition, but it's separable. And then the thing you note when you look over here is, well, the first term represents gravcat 1 on the left and gravcat 2 on the left. They're both displaced delta to the left, so they're 2d apart. But for instance, the second term represents gravcat 1 in the left state and gravcat 2 in the right state. So the distance between them is 2d plus a delta either side, so plus 2 deltas. So The interaction is a gravitational one, so there's going to be a different potential energy associated with this term compared to this term, right? And similarly for the other terms. So we just have an ordinary Schrödinger equation. We're going to assume the experiment, these things are heavy enough, and the experiment is short enough, and the forces are weak enough that nothing starts moving. There's basically everything in what I say is going to be in the static regime, effectively. So there's no kinetic energy terms. So the only energy that's going to show up in the Schrödinger equation is this potential energy. So it's just going to produce phases. But as you see, when I solve the Schrödinger equation, the time-dependent wave function is going to have different factors appearing. And so, but when I have a superposition with different phase shifts, as I do here, it's no longer going to be separable. This is an entangled state, and the only reason it's entangled is because of the gravitational interactions between the gravcats. Okay? So, what one would do sort of in principle then, if they have spins, put them back through the Stern-Gerlach apparatus. This would now amount to entanglement between the spins of the different gravcats, and that could be measured by, well, violations of Bell inequalities, or there's more sensitive ways of measuring things as well. So this entanglement could be observed. So it is about 5 years ago now people started talking about these experiments, and the claims, so these two papers in particular by Berzer and a whole group of people, and on the other hand by Moletto and Vedral, basically simultaneously, sort of putting the point in different ways, both of them claim basically doing an experiment like this, gravitationally induced entanglement, GIE. There's actually a bunch of names these things got called in the literature, but that's the one we're stuck on at the moment. Anyway, they say this would be a witness, and one might talk more about what a witness means, but in some sense an indirect measurement of the quantum nature of gravity. So that's the claim they wanted to make, and CNR, that this is Christodoulou and Ravelli. I'm going to talk about their paper in a minute. Also make this claim, for instance. Okay. Hopefully, okay, you see this is a kind of cool experiment, and it would be really nice if we could do this. But you might, at this point, sort of wonder about, that seems like an awfully sort of strong claim if you think about the way I actually presented it, because all I did was appeal to this, this potential. Well, it's quantum mechanics, so it's an operator, so I put hats on it, but it's not clear in this analysis in what way gravity itself is quantum. So that's kind of the question we need to look at.
What do you mean it doesn't look interestingly quantum? In the last sentence, I just didn't understand this.
So this is representing gravity in this analysis. Yeah, and maybe I should have said it, but because gravity doesn't look interestingly quantum, because that's all there is in this analysis. We don't usually think of the potential just because I put a hat on. I mean, of course it is quantum because it's an operator, but that happens like every time I write something down.
Yes, it looks just like any 1/r potential.
Yeah.
You interpreted as anything whatsoever.
I have to make it an operator because it's acting on quantum systems, but in itself it doesn't look, it's not clear how it's quantum. I mean, if someone wants to argue putting the hats on makes a profound difference, I'd be happy to sort of hear it, but I think it's not surprising people that, and I don't have a big axe to grind about that, but people are pretty skeptical about this. At any rate, there's purportedly a much more interesting way in which we have the quantum nature of gravity here. But moreover, we already have experiments where we have to put the hat on the gravitational potential. In the 70s, they did neutron interferometry experiments. using the Earth's gravitational field, then it's the same thing. You have to put the hat on the gravitational potential to make sense of that. Okay. So before we go into sort of unpacking what, what's actually being shown here some more in that regard, there is a very important feature of these experiments that if they were carried out and entanglement was observed, they really would, well, refute semi-classical gravity as a sort of theory of sort of everything in quantum gravity. Sort of the possibility of that has sort of exercised people, or put another way, it would definitively be the experiment would definitively be outside the regime of semi-classical gravity. And so the first time one actually had that in the laboratory. And I want to explain that because that is important. And this point is sort of independent of whether you think gravity itself is being quantum or not here. So consider semi-classical gravity. As I suggested before, we just takes the Einstein equation and following Müller and Rosenfeld, instead of the stress-energy tensor, you have to take the stress-energy tensor operator expectation value for the quantum matter. So this is because we want classical gravity and quantum matter. You can kind of postulate this as an ansatz, but there's also ways of kind of deriving this from quantum gravity as an effective field theory. And now think about the experiment from this point of view, using this equation rather than Schrödinger equation, as I did before. Okay? So we're now taking the expectation value, the stress energy expectation value for the quantum matter. So what does that mean? Well, here's one way you might think about it. If you think about it, the thing I'm going to say is independent of whether this is exactly the right analysis. But basically, a natural way of thinking about it is, well, I've got one grav cat in an equal superposition of sort of left and right around minus d. So its expected position is minus d. I'm taking them, and similarly, I've got one on the right, whose now expected position is d. So the expected matter distribution, is a grav cat at minus d and a grav cat at plus d. And that's what that's what's going to determine the gravitational field. And so from that point of view, grav cat 1 is whatever 2d plus delta. There's my 2d plus delta away from a source at d. The right component of grav cat 1 is, well, do the math, it's 2d minus delta to here. Right? Anyway, and so on for each of these. But the key point is, and now I'm not getting, whenever I have the left term, this is the phase factor the phase is going to be the exponentiated, it's going to be this exponentiated, whatever term it appears. Similarly for this, and similarly for this. So write it out, you can see, whenever my left appears, I have to write this potential, so here and here. Wherever my left grav cat 2 appears, here and here, it picks up the same potential. But these terms factorized to start with, there's one missing there, I never noticed that before. Okay. But because the thing originally factorized, and all I've done is multiply, every time I sort of have the same factor, the same term, I've put in the same factor. You can check it if that's not obvious. It's going to factorize again. It remains factorized. Okay? So, and I see. Something's gone, I see what's happened. This term should be up here. When I was editing the slides, that's obviously gone astray. So ignore that, that's supposed to be up there. And apologies to people on Zoom. there's a green, the green term in the second line is supposed to be on the left in the line above, where there's a tensor product with nothing there. Okay, all right, you can check it, but basically the point is, of course it's going to stay factorized because I don't get different potentials when I have left and left. This one sees the same potential whether GravCat2 is in the left or the right term because I've taken expectation values. All right, if you think about it, it's clearly, it doesn't matter. I just have basically a fixed potential sitting there, and that's not going to break the, that's not going to break the separability. It's going to stay separable. Okay, so that's the key feature here. Semi-classical gravity, because we're taking the expectation value, stress energy, is never going to produce any entanglement here. So if this experiment were done, or when this experiment is done, and when entanglement is observed, that will be a clear sign that we're outside the semi-classical regime here. So that's sort of a sense in which the experiment would show the quantum nature of gravity. But could we ask for more? And I can see I'm not going to have time to this, but there's something interesting here in the background is, well, as you may have detected from what I'm saying, almost nobody in the quantum gravity theory community thinks there's any chance of this being in the semi-classical regime. The only people who, well, there are some people who would think that there would be something funny going on here. So, you know, Penrose is the sort of the most prominent sort of example here. This is exactly the kind of case where he would expect that there to have been a collapse that actually would mean that there was no entanglement. This is exactly, if you know anything about Penrose DOC, this is exactly the kind of regime where there should be a collapse into one or other outcome. And we would not, again, he wouldn't predict entanglement either. Okay, but I would say basically almost everybody else in the theory community expects there to be entanglement and this to be a regime. Okay, sorry, I went off track a little bit there. But then there's an interesting question. If you're already sure that there's going to be entanglement, you know, there's lots of things in physics that we're really sure would happen if we did the experiment, and well, why do it? Shouldn't we do the experiments where we're not sure what's going to happen? I mean, here I am at the LSE. Shouldn't we be performing the experiments that have a risk of going wrong? And there's very little risk here. Okay, so do I talk for an hour, Brian?
You may do, yes. Yeah.
Okay.
You have another 20 minutes at least.
Yeah, okay, good. So, all right. I promised I'd go back and try to unpack the experiment from first principles a little bit more. And clearly, you know, the first principles are general relativity, quantum field theory, quantum gravity as an effective field, applying the techniques of quantum field theory to general relativity to try to quantize it. And that's where we're going to start from. And here's one way you might start from this, from such starting points. And this is this is from a paper by Anastopoulos and Hu from 2014. By the way, all these, well, hopefully all of them, there's a page of citations at the end of the handout, if you have it, and then you can actually find the papers there. So actually this paper was not on the GIE experiments. As you see, it's a couple of years before. It was actually about the Newton-Schrödinger equation, a critique of the Newton-Schrödinger equation. So another attempt to marry general relativity and quantum mechanics, and basically pointing out it is not what you get out of applying quantum field theory to general relativity. It's not one of the limits of that theory. It really is a different kind of theory. Okay, so this is going to work. This is how it works. If you've thought about it this will be sort of how you would expect things to go. So we start with general relativity, assume there's a scalar matter field, going to linearize, okay, you're going to take Minkowski spacetime, expand around, expand the gravitational field around there. There's going to be some gauge fixing. Again, you can read their paper if you want to see how this goes in a little more detail. But what you kind of, what comes out of it is the Hamiltonian that looks like this. Still GR, we're still classical at this point. Of course, there's a Klein-Gordon term that it captures the dynamics of the scalar field. This is the Gaussian constraint term. So this comes from the fact that we have a gauge theory. And, okay, and what does this one mean? Well, these epsilons, that's the energy density, and then I'm integrating over here, over these r's, I'm integrating over space. So this is basically a 1 over r term with sort of m squared in the numerator. So you can see that's going to be sort of Newtonian gravity term. After that, so Tij is the stress energy of the scalar field. These gamma ij's are going to be the perturbations of the metric. So those are gravitational wave terms. So there's going to be a term, of course, coupling these perturbations to the stress energy. There's going to be a self-interacting term, and then there are higher order terms in this Hamiltonian as well. Okay, very good. But for the GIE experiment, I said it's static. There's no other forces except gravity, so there's no kinetic term. There's no other interaction within the scalar field, so all the Klein-Gordon part drops out. But also, we're only interested in the first orders of approximation. There aren't going to be any effects involving gravitational waves. So none of those things are going to be relevant, and all that's actually left is this gauge constraint term. Okay. So that's all that's left. This is done classically. Now one quantizes, and then not surprisingly, of course, looking at this form, this term Hamiltonian in the GIE experiment then just reduces to, well, the very term that we used in the naive model. Okay. It's got a mass squared coming from the epsilons, and then a 1 over r term from the denominator. I mean, it's relativistic, so there's a constant mass term as well, but I'll just ignore that. Okay. So in fact, we get the same the very Hamiltonian. I mean, not surprisingly, if this weren't the case, then we probably we'd have done something wrong, right? This is the very potential, the very Hamiltonian that we were assuming in the naive model. But I'm going to differentiate what's done here from the naive model and call this the Newtonian model, because we're taking the Newtonian limit, precisely because I'm not just sort of postulating this Hamiltonian, this potential. Instead, we're now thinking of it as derived in this specific way from general relativity, applying quantum field theory methods. Okay, so that's what I mean by the Newtonian model. And now we think about, now there's some sort of interpretation that comes in, and this is where the questions of the significance of the experiment are relevant. So, as I said, this term arises from the gauge constraints in the theory. Doesn't involve any of what's called the true degrees of freedom in gauge theoretic terms. These, when we quantize, would become the graviton terms, excitations of the gravitational field, and they're just not relevant to the experiment, or at least the part of the experiment that I've described. None of that is sort of relevant then, according to this analysis. The only thing that is relevant is this potential term, this gauge constraint term. And moreover, this gauge constraint term, well, as you see, it's fully determined by the instantaneous matter distribution. There's no freedom in it. It's fixed once you have the matter field, so it's not dynamic. And moreover, it's non-local. It depends on the instantaneous distribution of matter. And so for that reason, people who like to model, think that the experiment should be modeled this way, are rather likely to, well, they do conclude, and Anastopoulos and a couple of other co-authors really have argued this way. This experiment doesn't really witness the quantum nature of gravity at all. Well, let me say it doesn't truly witness the quantum nature of gravity at all. It's just a gauge constraint, it's non-local. There's no physics here, the physics is not, the dynamics is not relevant to this case. Okay. So, I'm about to tell you the other model and the other interpretation that goes with that. But it's good to sort of say at this point, I've had, I get very different reactions from different audiences and different parts of audiences to what's going on here. Some who will be saying, yeah, of course, but that's not, so this is, of course, this is what's going on, and so, there's really nothing quantum about gravity here. Get that response quite strongly. People who think in the general relativity, so this is a very kind of quantum field theory way of thinking about what's going on, I would say. Other people have a very sort of strong reaction the other way, especially if they're thinking in terms of general relativity, and what kind of theory that's like. This is just completely the wrong way to think about the experiment. Right, so I'm going to tell you the other way, but that there are these strong, very strong reactions, and what that means or signifies, that this difference is sort of the point of the paper. So you'll have to wait for that. Some of you may be neutral, but those of you who are thinking, well, duh, why are you telling me this? This is obvious. Wait a minute. And those of you who are thinking, that's crazy. That's not the right way to think about it. Also, wait a minute. All right. So here's the other way, and this is exactly what you hear. Look, well, it took 100 years from sort of Maxwell and Faraday to, figure out the field concept and then understand gravity in those terms. Gravity is just sort of misdescribed radically here. What we've totally lost in that previous model is the fact that gravity is itself a dynamical, causal system. In some way on a footing, otherwise different, but we really have kind of brutalized our understanding of gravity by modeling it that way. What we should be doing instead is thinking about things from a different point of view. So, simple-mindedly, from sort of elementary sort of quantum mechanics point of view, what we need to be thinking is, we just went wrong by thinking, we've gone wrong by ending up thinking that we just have two matter systems and then a non-local interaction between them, because that totally misrepresents the scene. Obviously, what we really have is our gravcats. So gravcat 1 right on the left here still, and gravcat 2 on the right here. But there's a third system as well. This isn't a bipartite system, it's a tripartite system. There's got to be a state for gravity in here as well. All right, so the thing I've written down here is kind of very naive and assuming that tensor products work and everything. On the other hand, hence the simple-minded, on the other hand, I'll allude to it, there's a lot of thinking from quantum information theory in here, and I'll mention some of the sort of theorems that are coming from that are sort of brought to bear here, which really are thinking about it pretty much just like this, I would say. Okay, so what might these gammas be, I guess is sort of the question. How could we actually put some more sort of physics here? And again, the idea is one should be starting from general relativity and quantum field theory. I had just the Newtonian model. Here I have the tripartite models to indicate there are actually kind of a class of theories, class of models here that sort of have this basic form in common, but try to cash out what these gammas are supposed to be effectively in different ways. They're not really opposed to one another. I think they think of them as sort of complementary, just different ways one might describe the gravitational field. But again, all of them sort of starting with a quantum field theory and general relativity point of view, so really starting from the same considerations as the Newtonian model, with this as the key idea, rather than use gauge theory as the key idea. This is just sort of a very vivid one. I mean, the more I sort of talk about it with people, the more it seems like that maybe it's kind of more, it's quite heuristic, but still, it's quite sort of vivid for thinking about what's going on. So one proposal, and this is from the Christodoulou and Rovelli paper that I mentioned before, is these gammas are, we could think of them as I say here, the metric, quantum states representing definite states of metric geometry somehow, the one that's appropriate for each of the configurations. Okay, well, we're in the Newtonian limit, so the metric geometry you would sort of use then is just the sort of, is the static Newtonian limit, as I've written here. That would be the metric, and so this phi here, this is classical. This phi is basically a kind of gravitational potential term. Phi 1 is the one for gravcat 1, phi 2 for gravcat 2. So phi 1 is sitting in a potential where these are the potentials. Okay, that's the potential due to gravcat 1. That's the classical potential due to gravcat 2, as it were. Okay, and so big R is little r is the distance from the center of the gravcat. Big R is the radius of the gravcat. They're taken to be finite here. All right, it doesn't matter. This you just sort of, it's the metric you would expect in this limit. So this is the model that Christodoulou and Rovelli consider, and now each one of these terms sits in a different, has a different space-time metric, given by this expression here. Because of that, I mean, you can look at the details how how one will work this out. But the experiment now, because of the difference in the metric field, the experiments have different proper times. They all have the same phase per unit time that comes from the masses of the particles, but the amount of proper time that each of them propagates during the experiment is different, and surprise, surprise, you pick up exactly the same relative phases in the same way. You get the very same interference predicted, but now seen as a redshift in these different geometries. That's the idea. Okay. Well, very perhaps hopelessly naively, one now might look at these, maybe not hopelessly, but look at this state now, and now it seems, at least heuristically, really clear that we now have, if this is the right analysis of the experiment, it involves gravity as quantum, okay? Because I have a quantum superposition of classical gravitational fields in this way of thinking about things. And what could be more kind of quantum than that? So, all right, I did motivate this by talking about relativistic causality. It's not really relevant. If you do Newton-Cartan, we did a kind of Newton-Cartan analysis instead of a relativistic one, you get the same answer. The Burza et al. Paper that I mentioned, they do it in a different way. They think about coherent states of the gravitation, of the quantum coherent states of the gravitational, sorry, not quantum, coherent states in the other sense of a graviton field. Okay, coherent in the sense of quantum optics rather than that. Okay. So various ways of kind of model, and various other ways of modeling what's going on here, some of which are causal, some of which aren't. The point I want to emphasize is what's crucial is that you're thinking of there being two gravcats and an interaction mediating subsystem, which is gravity. so that it really is tripartite. That's how we think about it. So we're not going to end up just with a potential between them. It's going to be crucial that it's modeled with a mediator. So maybe it's worth saying, right, what I'm imagining is there's going to be a Hamiltonian and there's not going to be any interaction terms in that Hamiltonian between the two gravcats. The only systems that interact are gravity in gravcat 1 and gravity in gravcat 2. That's the kind of crucial idea here.
But so I'm just trying to understand, Nick, the gamma terms. When you write, you've written gamma LL, suggesting that it's in some sense appropriate for the situation where you have cat L on the left and cat L on the right, and
no, cat 1 on the left and cat 2 on the left.
Sorry, yes, yeah, cat 1 on the left and cat 2 on the left. Sorry, but if it's a vector space, if it's a quantum state, you know that gamma LL lives in a vector space, and so of course there is a vector which reads L cross gamma LR, say, cross L. And what does that mean in this context? It's like the formalism usually allows one to treat this as a wholly independent thing, so I can rotate that term from the gamma vector space to whatever I want. But is that not allowed here, or what sort of structure am I looking at? I'm just a bit confused.
So I think the thing you're pressing on, ask me again in a bit, okay? But you're pressing on exactly the way in which this is probably really heuristic rather than realistic, and one needs to look at some sort of more realistic kind of model of what's going on. Yeah, there's something kind of funny, right? Yeah. I don't know if you're kind of worrying about the gauge constraints that's here, because even this is sort of really still Newtonian, so it's gauge, so it's not like I could have had gamma LR here instead, right? I mean, fair enough. Fair enough. I think, ask me again and I can say a few more things about that. But you're pressing on just the way in which this is, yeah, kind of heuristic. Good. And I don't remember if you in the session at the PSA,
I don't remember.
This is what David was pressing on as well. So fair enough. But I do want to, but it's worth saying, although this, filling it out this way, and it's sort of heuristic, you know, this is still the way in which there, in some sense, the arguments people want to bring is, I don't worry too much maybe about the Ravelli crystal Ladulu. It's just, it is sort of heuristic. On the other hand, people on this side, the tripartite side, do want to bring this stuff to bear. It's basically, well, I would say it is a theorem of quantum mechanics that if you have a tripartite system that I described, so that there's no direct interaction between two of the terms, only with each of those with the middle term, that you cannot produce entanglement unless that middle mediating system is quantum. If it stays classical, you won't get any, you can't produce any entanglement. So I sort of know how to prove that in quantum mechanics. It's sort of an article of faith, at least, in the sort of large parts of the quantum information theory community. And you certainly can, there are theorems that are proved in regards to this, that really give you kind of an that was. So I've given some references here to Marletto and Vedrau and Giacomini, and I'm forgetting Galli, and anyway. So the Marletto and Vedrau prove theorems in constructor theory, so David Deutsch style constructor theory, which is a generalization of quantum mechanics. But if you get entanglement, the system, the mediating system can't be classical. It's not quite as strong as saying it has to be quantum. And this paper uses generalized probability theories to show basically the same thing. Actually, to say it has to be quantum is in fact too strong. There's actually counterexamples to that. But it has to be non-classical. Okay, good. But good. There is something I need to think through here. Maybe we can talk about it because, yeah, I want there to be enough of this picture left that we can actually meaningfully talk about this. And I guess this is something Mike's been pressing on a bit as well. Do I need to plug it in a bit?
Interesting, yeah. No, it was just plugged in, I doubt that. I wonder if it somehow got not clicked on the thing. Does it work now?
Yep.
Yeah, okay.
Great. Thanks. Okay. Okay. So, as you saw, this is the sort of interpretation part, and basically the situation as I presented it is we have sort of two models on the table about how to think about this experiment, one of which says we're really not seeing any interesting quantum behavior of gravity, one of which is saying, yeah, gravity has to be kind of quantum in this case. And I want to kind of make sense of that situation. So just to kind of recap, we have the Newtonian case that says this is, this gauge constraint is the only term that we have. So that's not quantum gravity. The tripartite case says, no, look, it's tripartite. That's the state we have to write down. And okay, heuristically, it's a superposition of gravity. Indeed, I've got theorems to show you that, if it's not a quantum intermediary, at least, or if it's a classical intermediary, we couldn't possibly be seeing any entanglement. So I might say, well, we want to know what the significance of this experiment is, so we have to decide which is the correct model here. Despite some people having sort of strong intuitions about which is the correct model, we would suggest that this may not even be a good question. In fact, stronger than that, it's not a good question. There's something kind of wrong with this question. We're talking about people who agree on the fundamental physics, so in some sense are not disagreeing about what's going on in this experiment in a fundamental way. Okay? What they're really disagreeing about is how to extract an appropriate approximation, an appropriate limit to actually describe this particular experiment from the point of agreement. So that doesn't sound like disagreement about as I sort of argued, the facts. It's an odd disagreement about something more subtle than that. Further, hopefully I've kind of you find both, even if you're passionately committed to one of these views, you can sort of see that what the other side is saying is not kind of wholly unreasonable, and if you can take a more neutral stance, I think you might, I think it's fair to say that both of these positions take reasonable theoretical stances, and so things seem to be theory-laden. Okay, but it's worth, and this is in a way what a lot of the paper does, is try to clarify what the competing theoretical perspectives are, try to state more clearly what the often unstated or implicit assumptions being made are, sort of reconstruct them, and then see whether they settle the debate. So I'll do a couple of slides to do that, and then I'll sum up. I'll take a couple of extra minutes for the questions, if I may. Okay. So Newtonian model. thing. So that applies standard gauge quantization to gravity. One way of taking the argument, and often sort of early when people were going back and forth about this, there's a certain amount of standard law interpretation of gauge theory. And let me just explain that and push back on that. So I summarize the argument, it's true. The true degrees of freedom, the fluctuations, the perturbations around the flat space-time aren't relevant to the experiment. Indeed, it's all just due to a Newtonian potential. There was a certain amount of, I think, confusion or misapprehension or misuse of the term true here early in the debate. So part of what I want, so let's just think about that. What does it mean that the true, defined to be fluctuations, perturbations around the flat solution or with the gauge fixed solution don't play a role? Well, things to see is partly this split is dependent on choice of gauge. Also, one should not read too much into the word true here. Clearly different potentials, different Newtonian potentials encode different physical content. Even though it's fixed by the matter field, it's not like there's no physical difference between different Newtonian potentials. Indeed, I hope this is the right one, until general relativity, the whole of gravity was just the Newtonian potential. So it would be very strange to say there was no gravity until we got general relativity, which is effectively what one would be saying is if one is saying there's no true physics in the gravitational potential. Hopefully you're thinking that would be quite a confusion to sort of say that in the first place, but that is the kind of rhetoric that sort of occurred in the debate. So there was a certain amount of confusion, I think, in the debate over the use of the word true degrees of freedom. There's a technical sense in which that's absolutely correct. The idea of a true degree of freedom, or the dynamical part of the theory, is well defined formally in gauge theory. That's a clear notion, but it doesn't mean the right sense of true or truly in this context. The potential is just as real physics. Okay, so that whole part of the debate, I think was just kind of confused, and I think was clarified quite without us, that people kind of figured their way around that part of the discussion, although you'll see traces of it if you look back in the literature. But what remains is, still is, I just have the potential with the hats. Is that really quantum or even non-classical? Especially since this really is the gauge constraint term. So that still is the intuition that's coming from the Newtonian paradigm, even stripped of this talk about true degrees of freedom. So assumptions on the tripartite model, okay. This starts from the assumption that gravity is an intermediary subsystem. Okay. But well, a couple of things someone might say. Let me just go over that. I'm just going to skip over that. If you want to ask, I can say some ways in which one might sort of try to say, no, that's not even true. Or that they, maybe not to say that it's not true, but to resist actually accepting that and being kind of neutral. But don't worry about it. I think the points, given the time, I'll skip to this next point. Right, okay. So we have the tripartite model. Gravity is really an intermediary subsystem. If you accept the quantum gravity approach, so the EFT approach, effective field theory, sort of effective quantization of general relativity as an approach to quantum gravity, then I think you have to kind of accept that at some level. And indeed, that actually is accepted generally by quantum gravity theorists, as I've said. including people who propose the Newtonian model. Right, clearly, that's exactly the assumptions that they're starting with in their model. So that's agreed. In fact, you don't even need to accept kind of quite that much. You know, there are these no-go theorems that have very weak kind of assumptions about what's going on here. Just that there's an intermediary, you don't need the full framework of the EFT. And if you believe that, then it's simply a theorem that what's going on in this, since we get into, assuming we get entanglement in the experiment, it just follows from quantum mechanics or the sort of more general approaches to quantum mechanics. The gravity just has to be in a quantum superposition. There just is no classical state that it could kind of be in here that would predict the entanglement. It's just impossible in quantum mechanics, let's say. Glossing over details. So this is what's then pushed back on the, by the tripartite paradigm to the Newtonian paradigm. So what's going on? Well, we're going to come back basically to what I said a minute ago. I think what's going on in the Newtonian, someone who advocates the Newtonian model then, over the tripartite model, is, yeah, sure, in some sense, really what's going on, in some sort of deeper level, gravity is behaving in a quantum way. But that's happening all the time. I believe in the effective field theory approach to quantum gravity. So every gravitational field, the ones that look classical in some sense are quantum. The question is a different one. It's whether I'm actually seeing the quantum nature of gravity and a characteristically quantum nature of gravity in this particular experiment. And I think one might push that line of thought sort of further, sort of thinking about how to extract models from underlying physics. Maybe there's some kind of maxim, right? What one does in physics is idealize, and what one should do in physics is idealize as much as possible and still get the prediction. The whole point is to get rid of the unnecessary details, and that's what pushes the Newtonian model. Forget all that tripartite stuff. This is the simplest model we can kind of come up with. Okay, and then it's also further motivated. It's just a gauge constraint. And moreover, I'm not just being difficult here. I'm now talking in the voice of the Newtonian. I'm not just being difficult. I can tell you some things that I would accept as showing the quantum nature. For instance, do that decoherence experiment. Then I would buy it. Okay, all right, I'll just put that up. And is that it? I think that's it. So that one. Just come to the point. Turning to Kuhn, which sort of will upset some people. Not the Kuhn of structure, the Kuhn of objectivity, value judgments, and theory choice, I think describes a situation kind of much like this, where scientists can agree about a whole lot of things, but weigh things differently, weigh the importance of things differently, and come up to different conclusions, and there can be no way of sort of algorithmically, objectively settling the dispute between them, even though they're both being sort of fully reasonable, and indeed in ways that they should be able to recognize from each other. And that's kind of what I think is going here.